Hello guys, in this Kirchhoff's current law, we have looked on the voltage law, okay? That the sum of the currents entering any junction must be equal to the sum of the currents leaving the junction. So we are saying, using this diagram that we are having, okay? So using this diagram, we are saying we have a junction at BD, okay? So we have, um, I'll just indicate this. So I'll say we have a junction at BD. Okay, so we have a junction at BD and we have three branches connecting the same junction. So we have three branches. So we have three branches connecting these junctions, and the branches are, so we have the first branch as BAD. We have the second branch as BCD, and the other branch as BD. Okay, we can maybe just take a look. So we are saying we have this junction A, we have B, okay, we have BAD, okay, BAD. We are going with the flow of the current. The flow of the current is to this side, okay, for the first branch. So we have this branch, and then we have now this other branch, which we are saying B, C, D. So the current is moving to this side, okay? And again, we have this other branch. Now we are saying for us to get the current in this branch, we are saying uh, we have two junctions at BD and the three branches are that. So the current in the branches will say will have to use the Kirchhoff junction rule, which says that the current entering through a branch must be equal to the current leaving the same branch or the junction. Okay, so our first step is, if we choose the left loop, so this is our left loop. So if we choose this left loop uh, and the right loop, okay, so if we choose this left loop and this right loop, then we transverse the left hand loop in the counterclockwise direction from point B. Okay, so if we traverse this from point B in the counterclockwise direction, so we'll go to this side. Okay, so this is counterclockwise. Okay, so if we go to this counterclockwise direction and we're transversing, remember we're transversing the left hand loop. Okay, so we will say if we go through this side using, remember the EMF rule from our first video, we are saying should be positive. Okay, so it should be +1 at this point because the current is moving in the same direction as the EMF arrow. Then at this point the current is moving in the direction for the move through the resistor, so it should get a negative IR1. Okay, then we are saying I'll add that to, if I move to this point, now I'm getting back to my B. Okay, I'm using this left hand loop. Okay, so this is the left hand loop. Okay, so if I'm using this, the current is moving through this side, so I'm already at point D. So at point D getting back, as you can see, the current comes to this side. Okay, so this current, it's not the full current that's entering at this point. Okay, the reason is there's some current moving to this other side also. There's a junction at this point. Okay, so this junction splits the current into two parts. Okay, so there will be a minimal current through this point. So I'll say the current total should equal current 1 plus current 2. Okay, at this point, now we're saying there's some current moving through R3, but in the opposite direction, so should be positive IR. Okay, so positive IR2. So all these complete traversals on the potential energy should equal 0. Remember, so we're saying we are moving from B to B. Okay, through that. So we're saying for the bigger loop, so this is the full loop. So this is for the left hand loop. Okay, so for the left hand loop, we are having that. So for the bigger loop, okay, So for the bigger loop, remember it's now the whole circuit. We will get E1 minus IR1 minus IR2, okay, minus E2 equals 0. Okay, so maybe just to show that, we're saying for the bigger loop, we are going the we're going to the counterclockwise direction. Okay, so we are moving from point B and now traversing not through junction B but now through the whole circuit. Okay, so we'll move from this point, and to this point is positive, so I should get a positive at this point, as you can see. So from this point I should get negative IR because it's towards the direction of the resistance. Now from this point the potential is 0 over the wires. So at this point we are getting it in the same direction with the I, so I should get negative IR. Okay, so at this point it's now in the opposite direction with the direction of the potential. Okay, the direction of the potential, the direction of the EMF arrow is in the opposite direction with the current at this point. So this current moves to this direction. Now this should get negative. Okay, so from this point we are seeing from the bigger loop we are getting that equation. So why are we doing this? So we are saying uh, this concept, this setup enables us to calculate the resistance in series and the resistance in maybe parallel. Okay, for this case it's just in parallel. So for us to calculate all the resistance in parallel, so we'll say the resistance in parallel, resistance in parallel. So for this, for us to calculate the resistance in parallel, as we have seen, this Kirchhoff's rule allows us to calculate two things. Okay, we can calculate the resistance, the total resistance in a loop of circuit, a multi-loop of circuits. Okay, so we can get the expression for the R equivalent, and we can also get the expression for the total current in the circuit. So for this case, we are saying all resistors, okay, all resistors have the same potential. Okay, all the resistors have the same potential. Okay, so from this point we are saying uh all these resistors have the same potential, so we are saying have the same V. Okay, so let's calculate that. So we are saying deriving for the expression for now R equivalent. Okay, we'll say from Ohm's law we know that current is the same as voltage upon resistance. Okay, that's for our first, this is now for our first resistor at this point. We are saying, so for our second resistor we'll get I equal V upon R2, and again for our third resistance, so this is the first current. Okay, so this should be the first current passing through the I1. Okay, then for this point it's I2. So for this case you're getting I3 should get V upon R3. Basically I'm saying for me to get the current at this resistor, I'm saying I1. Okay, I1 should get, because the voltage are the same, so we just write the same V. Okay, so for this is the total current. So this is the first current, and this is the second current, and this is the third current through all the resistors. So for us to get the total current, now applying the Kirchhoff's rule. So I'll say applying Kirchhoff's current law, we are saying we should get it's saying we should get the total current as the total current entering a junction should be the same as the total current leaving out the junction. So the total current here will have to add. Okay, so we'll have to add the first current, added that to the second current, and added that to the third current. Okay, so let's complete this. So we are saying what's my first current here at this point? It's V upon R1, then add that to V upon R2 and add that to V upon R3. So pulling out my V, I should get I total. So I'll say I total. I total should get me V into 1 upon R1 plus 1 upon R2 plus 1 upon R3. Okay. So once you have calculated that, so we have seen the total current in the circuit to be this. Okay, so this is the total current in this circuit for this case. So as you can see, the Kirchhoff's junction rule helps us to calculate the total current in the circuit. Okay, so once you've calculated that, let's keep in mind, we know that from the Ohm's law, we are saying current equal voltage all over the total resistance, the resistance equivalence. Okay, so we are saying calculating this, we are saying 1 upon R equivalent is the same as 1 upon R1 plus 1 upon R2 plus 1 upon R3. Okay, so we're saying from this expression, we are getting this as our answer. So we are saying the R equivalent, which is 1 over I R equivalent, should give me 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this is the total resistance in parallel. Okay, so this is how we derive the total resistance in parallel. For us to calculate the resistance in parallel, we should get the expression for this. So this is the expression for the resistance in parallel. So from this point, we're saying, what if we are having several resistors? Okay, so for a number of resistors, say n, we'll use the expression 1 upon R equivalent should equal the total summation, okay, from n equal 1 to n. Okay, so this should be I, sorry. So from I equal 1, so from I equal 1 to this, then I should add 1 upon Ri. So this is for several circuits. So for two circuits, we're saying for two circuits, we are saying the total resistance will just equal the resistance equivalent will just equal the resistor 1 multiply that by the resistor the second resistor, then divide that by the summation of the two resistors. Okay, so this is how we calculate the resistance of two resistors in parallel. Okay, the reason is because V is the same. Okay, we're saying at this point also the V should equal the same. Okay, so please like, share, subscribe to my channel, follow for more. Thank you.